Değerli katılımcılarımız, hepiniz hoş geldiniz. Öncelikle katılımınız için teşekkür ederiz. Seminerimizi planladığımız şekilde soru cevap dahil olmak üzere 90 dakikada tamamlayabilmek için başlayacağız. Ancak katılımlar devam ediyor. Sunum kaydedilecektir. Konunun bütünlüğü açısından soru cevap sunumun sonunda yapılacaktır. Ancak siz lütfen dilediğiniz zaman aşağıda bulunan Q&A ya da chat kısmından mümkün ise hangi konuşmacıya sorunuzu yönlendirdiğinizde belirterek bize iletebilirsiniz. Bugünkü seminerimizin konusu lipozom, lipid nanopartikül ve benzeri veziküllerin Microfluidizer teknolojisiyle verimli bir şekilde üretilmesi. Sırasıyla ben Mecra Kılıç Arslanlar, şirket tanıtımları, Microfluidizer teknolojisi, çalışma şekli, avantajları, uygulama alanları, alternatif teknolojilerle karşılaştırılması, ölçek büyütme ve ürün grubu, pilot, üretim ve laboratuvar olmak üzere anlatacağım. Akabinde sözü Microfluidics'te uygulama mühendisi olarak çalışan arkadaşım Küçük'e vereceğim. Kendisi lipozomlar, kullanım alanları, aşı uygulamaları, ilaç taşıma sistemlerinden ve lipozom formülasyonlarından ve hazırlama şekillerinden bahsedecektir. Ayrıca kendisi bizim için laboratuvarda cihaz ile çalışmayı anlatan kısa ama bilgilendirici bir video hazırladı. Sunumunu da izleyeceğiz. Bunun için kendisine teşekkür ediyoruz. Ayrıca gerçek örneklerle bize detaylı olarak teknolojinin başarısını anlatacaktır. En sonunda da soru cevap kısmına geçeceğiz. Karşılıklı güzel ve faydalı 90 dakika geçirmeyi diliyorum. Bu arada bugün bizimle yeni teknolojiler ve uygulama müdürü Microfluidics firmasından Nasıl da birlikte olacak. Ayrıca bölge sorumlumuz Christina Schneider da bizimle. Soru cevap kısmında görüşeceğiz tekrar. Hazırsak başlayalım. Öncelikle tanıyanlar ya da tanımayanlar için Anametanalitik Grup'tan bahsetmek istiyorum. Anametanalitik Grup 1975 yılından beri pazar lideri olarak satış ve satış sonrası hizmetleri yürütmektedir. Bunu tabii sürdürülebilir bir şekilde yapabilmesi için çok yakın ilişkiler kurarak ve en uygun çözümleri geliştirerek birlikte müşterilerimizle birlikte geliştirerek bu süreçleri ayrıca sürekli eğitimler hem ekibimizle hem de müşteri eğitimlerimizle beraber bu başarıyı yakalıyoruz. En kaliteli hizmeti vermeye çalışıyoruz ve gerçekten elimizden gelenin fazlasını yapmaya çalışıyoruz müşteri memnuniyetini sağlamak için. Kuruluşundan bu yana elbette portföyü çok olmamakla beraber özellikle 2000'li yıllardan sonra pazarın da gereksinimleri doğrultusunda gelişmektedir. Microfluidics firması da onlardan biridir. 2000'li yıllardan sonra birlikte çalışmaya başladığımız çok başarılı bir şirkettir. Onun dışında ama Milestone, Bühi, Elga, Thermo, Integra, Sotax, Bühi Glasuster gibi pazar liderleriyle çalışmaktayız dünya çapında. Microfluidics firmasıyla bahsetmiştim. Biz 2000'li yıllardan beri çalışıyoruz ama 82 yılında kurulmuş bir firma Amerika'da, merkezi Amerika'da. 2011 yılında IDEX grubu tarafından satın alındı ve materyal işleme teknolojileri platformuna adapte edildi. Burada aynı faaliyete devam etmekte ve mikro akışkanlaştırıcı işlemciler nerelerde kullanılıyor? Aktif farmasötik bileşenlerin, aşıların, püskürtmeli mürekkeplerin, kaplamaların, nütrosyotiklerin ve kozmetiklerin özellikle Ar-Ge'sinde ve üretiminde kullanılmaktadır. Onların şöyle bir sloganı var, müşterilerimizin başarısı bizim başarımızdır diye. Bunu zaten anlatmaya çalışacağız. Bugün gerçek örneklerle size anlatmaya çalışacağız. IDEX firması ise yine Amerika merkezli bir firma. New York borsasında işlem gören ve 5 kıtada 5000 üzerinde çalışanı sahip büyük bir şirket. Bunun çatısı altında devam etmektedir Microfluidics firması. Microfluidizer teknolojisinden bahsetmek istiyorum. Neyi iyi yapıyoruz? Uygulama alanları nelerdir? Bakacak olursak nanoemülsiyonlar, hücre parçalama, polimer nanopartiküller üretme, lipozomlar bugünün konusu, parçacık boyutu küçültme, dağılma, moleküler ağırlık azaltmak gibi uygulama alanları var ve bunu laboratuvar ölçeğinden pilot ve üretim ölçeğine kadar hizmet verebilmekte. Bu başarıyı tabii nasıl yakaladığını teknolojiyi anlattıkça sizinle beraber göreceğiz, inceleyeceğiz. Burada tabii müşterimizin bir görüşüne yer verdik ki çok değerli bir görüş. Özellikle de bugün üzerinde duracağımız bir konu. Çünkü laboratuvardaki Ar-Ge çalışmalarını birebir olarak modifiye etmeden üretimde kullanılabiliyor olmak, adapte ediyor olmak çok büyük bir avantaj. Bahsettiğimiz gibi 1 mililitre dahi işliyor olsanız ya da binlerce litrede işliyor olsanız aynı kesme işlemi uygulandığı için sonuçlar da aynı olmaktadır. Bunu ilerleyen slaytlarda yine gerçek örneklerle anlatacağız. Dolayısıyla da sonuç olarak steril filtrelenebilen nano emisyonlar elde edebiliyoruz. Özellikle hücre parçalamada en yüksek düzeyde protein geri kazanımı sağlıyor teknoloji. Ve elbette en çok istenilen, hedeflenilen uniform parçacık boyutuna getirebilmekteyiz. Şöyle bir şematik olarak bakarsak çalışma prensibine bir giriş haznemiz var. Akabinde hemen bir pompamız var, güçlü bir pompa. Ve asıl kalbi, yani sistemin kalbi diyebileceğimiz etkileşim odası. Bunda ayrıntılarına bakacağız. Etkileşim odasından sonra da eğer gerekiyorsa özellikle sıcaklık kontrolü için bir ısı değiştirici koyabiliyoruz. Ve ürün çıkışı yer almaktadır. Bunu bir fotoğraf üzerinde görürsek de giriş haznesi genellikle cam, standart olarak camdır. Bir yoğunlaştırıcı pompamız var. Akabinde etkileşim odasına besliyoruz ve burada çok kısa süre kaldıktan sonra ısı değiştirici ya da ürün toplama bölümüne gelebilmektedir. Bu teknolojinin tabii özellikle en büyük vaadi uniform ve ölçeklenebilir sonuçlar elde etmek. Bunu da nasıl sağlıyoruz? Aslında iki faktörle sağlıyoruz. Sabit basınç ve sabit geometri. Ne demek istiyoruz? Şimdi bunu birazcık açmaya çalışacağım. Burada kullanılan teknoloji, pompadaki teknoloji bir piston yardımıyla piston ileri ve geri hareket eder ve çok hızlı ayarlanan basınca ulaşabiliyor ve uzun süre bu basıncı koruyabiliyor. Sonra basınç sıfıra düşüyor. Bu grafik çok önemli bir grafik. İlerleyen slaytlarda yine göreceğiz ölçek büyütmede de. Çünkü aynı teknolojiyi kullanıyor olacağız. Ve neredeyse numune ayarlanan basınçta proses edildiği, işlendiği için sonuçlarda mükemmel olmaktadır. Bahsettiğim gibi pilot ve üretim ölçeğinde de bu sefer çift pistonla çalışıyoruz. Bu daha da önemli bir avantaj getiriyor partikül boyutu açısından. Bunu da anlatmaya çalışacağım. Etkileşim odasına eğer bakarsak, yani sistemin kalbi diyebileceğimiz, içinde mikrokanallar olan etkileşim odası gerçekten şekil itibariyle de Y tipi ya da Z tipi olarak ayrılıyor. Her ikisinde de yüksek etki bölgesi ve yüksek kesme bölgesi olmak üzere bölgeler bulunmaktadır. Tabii aralarında özellikle aplikasyon açısından farklılıklar var. Y tipi emülsiyonlar ve lipozomlar için kullanılırken Z tipi ise süspansiyonlar ve hücre parçalamada kullanılıyor. Ayrıca tabii aşınmaya dayanıklı olabilmesi için seramik veya elmas olarak tercih edilebiliyor. En önemli avantajı elbette az bakım gerektiriyor olması. Temizlemek çok kolay, bir temizleme çözeltisiyle temizleniyor. Çok hızlı ve efektif bir geçiş sağlanıyor pompalar sayesinde de. Basıncın yüksek olması yüksek kesme hızını da getiriyor. Grafikten de görüleceği üzere. Farklı etkileşim odaları kullanıyor olsanız bile pilot üretim ölçeğinde dahi çok yüksek kesme hızlarına ulaşabiliyoruz. Dolayısıyla alternatif teknolojilerle karşılaştırdığımızda özellikle en yakın teknoloji homogenizer, genel adıyla homojenizatör olarak veriliyor ama çok kat daha üst, daha büyük kesme hızlarına ulaşabiliyor Microfluidizer işlemciler. Biz genellikle aslında homojenizatörleri ya da diğer alternatif teknolojileri premix ya da ön karıştırma için de kullanabiliyoruz. Onlardan faydalanabiliyoruz hala. Örneğin burada bir valfli homojenizatör örneğini görüyoruz. Buradaki tabii en büyük belki handikap, manuel olarak bu valf hareket ettirildiğinde sonuçlar kişiye bağımlı olabilmekte ve çok da uniform bir dağılım elde edilememektedir. Buna karşılık az önce bahsettiğim şekliyle fosil profilinden dolayı yüksek kesme hızlarına da numune içeride kaldığı sürece maruz kalıyor ve dolayısıyla da bunu partikül boyutu verisinde gözlemleyebiliyoruz sonuçlarını. Örneğin 1, 2 ya da 5 geçişten sonra yeşille partikül boyutu dağılımına bakarsak Microfluidizer için çok daha dar bir partikül boyutu dağılımı görüyoruz. Homojenizatör teknolojisinde ise çok da uniform olmayan geniş bir dağılım elde ediliyor. Sonuçlarına bakarsak rahatlıkla şunu söyleyebiliriz. 5 geçişten sonra bile aslında homojenizatör Microfluidizer'ın tek geçişine ulaşamamaktadır. Ve uniformiteye baktığımızda çok daha dar bir partikül boyutu aralığında elde ettiğimizi söyleyebiliriz. Ölçek büyütmeye gelince tabii bu çok kritik bir konu, çünkü laboratuvarda yapılan çalışmalar genellikle üretime ya da pilot üretime aktarılırken çok ciddi mühendislik gerektirir. Ancak bu teknolojide değil. Çünkü aynı etkileşim odalarını çoğaltarak yapıyoruz ölçek büyütmeyi. Dolayısıyla aynı kesme hızı, aynı etki kuvvetiyle aynı parçacık boyutuna ulaşabiliyoruz. Hatta daha iyisine ulaşabiliyoruz. Sebebini de birazdan açıklamaya çalışacağım. Örneğin bir aşı adjuvan emisyonu örneği üstünde görebiliriz. Hem laboratuvar ölçeğinde hem de üretim ölçeğinde neredeyse aynı partikül boyutuna, hatta daha küçük partikül boyutuna ulaşılmış durumda. Mavi ve mor ya da fuşya renkli grafiğe bakarsanız birbirinin üstüne çakıştığını görebilirsiniz. Geçiş sayısıyla beraber. Dolayısıyla da partikül boyutu dağılımında da çakışan bir grafik görüyoruz. Hatta çok daha küçük bir partikül boyutu dağılımına ulaşabiliyoruz üretim ölçeğinde. Microfluidizer ürün grubuna kısaca bir göz atabilirsek, bahsetmiştim. Laboratuvar ölçeğinden başlayıp pilot ve üretim ölçeğine kadar sunabiliyoruz farklı cihazlar. Tek tek cihaz modelleri üstünden gitmeyeceğim ama kabaca şunu söyleyebiliriz. 1 mililitre ile başlayabiliyoruz ve dakikada 330 mililitreye kadar akış hızını sağlayabiliyoruz. Bazı modeller hava kaynağına ihtiyaç duyar, bazıları tak ve çalıştır özellikle kendi içerisinde kompresöre sahiptir. Pilot ve üretim modellerinde ise yine 2000 bara kadar çok güçlü basınçlara kadar ulaşabilmek mümkün. Böylelikle ölçeği büyütmüş, hatta üretime taşımış oluyoruz. Bir de biyofarma versiyonları bulunmakta. Bu ürünlerin özellikle GMP regülasyonlarına uygun olabilmesi için bu seçeneklerimiz de mevcut. Size güzel bir görselle bu kısmı bitireceğim. Üretimden bir görselle. Bu kısımdan sonra sunuma Chris devam edecek. Good morning, Chris.
Hi, good afternoon.
I know it's very early in the morning for you. Yeah, we really appreciate your effort and time. And thank you for preparing a very nice video in your lab. So we are very excited to hear about the liposomes technology and advantages, success stories at your customers. So I'm leaving the words to you.
Awesome. Yeah, thank you, Nijla.
Thank you.
Yeah, as you mentioned, today I'll specifically be focusing on liposomes. I'll specifically be discussing how they're manufactured utilizing a microfluidizer processor, and we'll be getting into a couple of case studies as well. So to start, I'll just start with a relatively high-level overview of liposomes, what exactly they are and why they're beneficial. So as you can see kind of listed here, liposomes are spherical lipid vesicles with a bilayered membrane structure. So they're composed of lipids, which are molecules similar to the one shown here, where they have a hydrophilic head and a hydrophilic head and a hydrophobic tail. And these lipids actually have interesting properties where if they're formulated under the correct conditions, they self-assemble to form these liposomal structures. So this is a cross-sectional area shown right here of what a liposome might look like. Again, you have the hydrophilic head shown here and the hydrophobic tail shown here, and they form, again, these bilayered structures. So liposomes are one of the most successful delivery systems currently in clinical use, and this is the case for a variety of reasons. One of the major reasons is that they can encapsulate either hydrophobic or hydrophilic actives, or even both. So if it's a hydrophilic active, it can be loaded inside of this aqueous core, whereas if it's a hydrophobic or lipophilic active, it can be loaded inside of this bilayer itself. There's a variety of other benefits for using liposomes as well, including that they can encapsulate the drug and kind of protect them from external conditions. Liposomes can be functionalized for targeted delivery. They can be pegylated to increase their circulation half-life. You can vary the formulation, including the composition, size, and surface charge in order to achieve your end goal with that specific liposomal formulation. And they can also be used for both active or remote drug loading, meaning you can load the drug while you're forming the liposome itself, or you can essentially first form an empty liposome and load the drug after the fact. So one brief caveat I want to give about this presentation is a majority of the applications that we'll be discussing today will be around the pharmaceutical industry, but the same principles that we'll be discussing for these examples can also be applied to several other industries as well. We've specifically noted the cosmetic and nutraceutical industry. So speaking of the pharmaceutical industry, there's really two key applications for liposomes within this industry, and that is for both vaccine and drug delivery. So as you can imagine, with these two different applications, they both kind of have different end goals. So for example, for a vaccine formulation, one of the goals is that you would want high immunogenicity, meaning that you would want to elicit a good immune response. While this is not necessarily the case for drug delivery. So it's important to kind of highlight these end goals and know what the goals of these formulations are, so that when you're considering kind of some key considerations, such as the lipid selection and the vesicle size, you can do so with an eye towards the goal that you're actually pursuing for that particular liposomal formulation. So when you make these key considerations, they can kind of lead to certain attributes for certain formulations. So for example, for a vaccine formulation, some certain attributes that you might be looking for would be to target and stimulate some antigen-presenting cells. You want to protect the antigen itself, improve the pharmacokinetic profile, and a delayed release can also be beneficial as well. Whereas for a liposome formulated for drug delivery, the attributes might be slightly different. You might want to focus on passive drug targeting. You could also improve a pharmacokinetic profile. You might be focused on slow release and actually solubilizing the drug itself. So I'll get into the formulation side of things in a little bit more detail on a later slide, but we do just want to draw your attention to the fact that we worked in conjunction with our collaborators at the University of Strathclyde to put on a webinar a few years ago, kind of specifically discussing these considerations and how they affect the attributes for both vaccine and drug delivery. So if you're interested in learning more about that, we've included the URL in this slide, so feel free to visit that. And then real quickly, I just wanted to give a couple of examples of current products that are on the market utilizing liposomes for vaccine delivery. Specifically, two of the major ones are actually both manufactured by GSK, and they are Shingrix, which is a shingles vaccine, and Mosquirix, which is a malaria vaccine. And both of these vaccines actually utilize the same AS01 liposomal adjuvant. And then just to give a couple examples of current formulations that are on the market, or current products that are on the market that utilize liposomes for drug delivery. One is Doxil, which is liposomal doxorubicin. So this formula, or this product, is utilized to treat several different kinds of cancers, including breast and ovarian cancer. Another one that's on the market is Ambisome, which is liposomal amphotericin B. And this amphotericin B is used to treat several different types of fungal infections. Visidyne is another example, which is liposomal verteporfin, which is used to treat macular degeneration. So again, these are just a handful of examples of both kind of liposomal vaccines and liposomal drug delivery systems that are currently on the market, but there are several other drugs that are currently on the market as well. So now getting more into the formulation side of things. As I mentioned, these liposomes are composed of lipids, but more specifically, they're typically composed of phospholipids, especially phosphatidylcholine or PC. And these phospholipids can be kind of derived from a variety of sources, but one of the more common sources is from lecithin. So lecithin is a naturally occurring material that can be derived from sources such as egg, soy, or sunflower seeds. And lecithin kind of contains a high level of phospholipids, so it's a pretty useful source to obtain these phospholipids. It's important to note that when you're formulating your liposomes, you can either use a single phospholipid or a mixture of phospholipid, and that the liposome formulations tend to include additional kind of components as well, a common one being cholesterol. And while cholesterol doesn't actually form the bilayer itself, it can actually be incorporated inside of this bilayer, and it can affect certain liposomal properties, such as the membrane fluidity, elasticity, and permeability. So on this slide, I've listed a few common lipids that are used in liposomal production, along with a few of their characteristics or properties. What I specifically want to draw your attention to on this slide is this transition temperature. So this is a very key characteristic to keep in mind, as when you're handling these lipids in order to form your liposomes, you're going to want to do so at around at least 5 to 10 degrees Celsius above the transition temperature of the lipid itself. And the reason for this is that when you're above the transition temperature, that is when the lipids are most fluid and will actually be able to self-assemble into those liposomal structures. If you're below the transition temperature, the lipids are more rigid and kind of in a solid state, and they will not actually form the liposomes. So that is one key characteristic to keep in mind when you're trying to determine which lipid you would like to use to form a liposome. But there are several other properties that you might want to keep in mind as well, kind of including this fatty acid number, which is the ratio of a number of carbons in a fatty acid chain to the number of double bonds in a fatty acid chain. And you might want to keep in mind the charge of the lipid as well. All of the lipids we have listed here kind of have a neutral charge have a neutral charge at net pH 7.4, but there are certain formulations where it might be beneficial to have either a positive or negative charge. Specifically, cationic lipids are fairly common in the formulation of liposomes. So now we're going to get into how to prepare the liposomes utilizing a microfluidizer processor. But first, I wanted to quickly run through kind of the different categories of liposomes. So there's 4 major categories of liposomes, and they include both small unilamellar vesicles and large unilamellar vesicles. So as these names might suggest, they're unilamellar, meaning that for both the SUVs and LUVs, they consist of only a single lipid bilayer. And then obviously the difference between the small and the large is the size of the vesicle itself. The exact definition kind of varies depending on where you're looking, but as a general rule of thumb, we kind of consider anything under around 150 nanometers to be an SUV. There are also multilamellar vesicles. So in this instance, you have multiple lipid bilayers kind of forming inside of another lipid bilayers in sort of this concentric circle structure. And there are also multivesicular vesicles as well, or MVVs, where you have lipid bilayers being formed inside of other lipid bilayers, but not necessarily in a concentric structure. So it's important to note that when you're utilizing a microfluidizer processor, typically you'll be preparing first MLVs, and you will be using the microfluidizer processor to size reduce down to SUVs. And to show what that might look like, I have a little schematic down below. So again, when you're utilizing a microfluidizer processor in liposome production, we utilize what we refer to as a top-down method, which again is just size reducing these liposomes. So first, what you would want to do is hydrate your lipids. So there's several methods that can be utilized to do so. The most common, or the one that we see most frequently, is a thin film hydration method. So the thin film hydration method consists of dissolving your lipids in a solvent in order to get a homogeneous mixture. Then you would evaporate off the solvent, and what you are left with is a thin film of lipids. So you can then take this film, hydrate the lipids, and utilizing a high-shear premixer such as a rotor-stator mixer, as long as you're doing so, again, above the transition temperature. When you're hydrating the lipids, they will form these MLVs. At this point, you can then process through the microfluidizer processor, keeping in mind some of the key processing parameters that need to be optimized, such as the choice of the interaction chamber, the processing pressure, the number of passes, and again, you want to make sure that you're processing above that transition temperature of the lipids that you're using. And then assuming that you've properly formulated and properly optimized the processing conditions, again, you'll be left with these SUVs. So that's kind of a brief overview of how you would utilize a microfluidizer processor to manufacture liposomes. But for more of kind of an in-depth view and to kind of see a microfluidizer processor actually operate, we've actually shot a short video here, which Eunice will pull up and we can hopefully play for you. Today I'm going to be showing you how to process liposomes on the LM20 microfluidizer processor. Before we process the liposomes, I'm first going to quickly walk you through how the LM20 microfluidizer processor operates. So to begin, you would load your sample into the inlet reservoir. We currently have water in the inlet reservoir, which we will use to prime the system. But once the system is primed, again, this is where you would load your inlet sample. Once your sample is poured into the inlet reservoir, we will begin by turning on the motor and then the intensifier for the system. So it's a pretty simple system on the LM20 where it is a touchscreen that you use to both start the motor and the intensifier. So essentially what we will do is we will set the processing pressure. We currently have it set for 30,000 psi, which is the processing pressure that we want. So we're going to go ahead and enter that. And then once we want to start processing, we'll turn on the motor and then the intensifier. Once the motor is on and we turn on the intensifier, the pressure will build in the microfluidizer processor, and then the plunger will retract, drawing some sample in, and then it'll push forward to force your sample through the interaction chamber. So we currently have an F12Y interaction chamber set up on the LM20 microfluidizer. This is a 75 micron interaction chamber. So once the plunger forces your sample forward, it'll pass through the interaction chamber and then through this cooling coil and then into the outlet. When we're actually processing the sample, we will load the sample tray with an ice water bath to keep the product temperature down, as when you are processing on a microfluidizer processor, there is a slight temperature increase. Before we start processing, I'm going to quickly show you how to prime the LM20 microfluidizer processor. It's a pretty basic system that is used to prime this machine. What we're going to use is essentially use this stick to depress the check valve, which is a ball on a spring. What this does is this will remove all of the air from the system, and once we stop seeing bubbles, then we can be confident that all of the air has been removed from the system. So I'm going to simply place the stick and depress the check valve, and you can see a lot of the bubbles coming up. The bubbles have stopped, so we can be confident that the system is primed. So now that all of the air has been removed, I'm going to start the motor and then the intensifier to essentially flush this water through the system. So first I'll set the motor. and then the intensifier. And I brought the water level just above this inlet check valve so that when we introduce the actual liposome sample, we will minimize the amount of dilution. So here we have a premixed sample. Typically, liposomal samples can be premixed in one of two ways, either via film hydration. In this case, you would create a lipid film and then hydrate the film and mix above the transition temperature with either a high speed or a high shear preprocessor. The other common method used to premix liposomes is simply adding the lipids to the aqueous phase and also allowing proper hydration time, mixing, and ensuring that you're processing at the transition temperature. So when you're processing on a microfluidizer processor, you are reducing the size of the liposomes, essentially going from large multilamellar vesicles to small unilamellar vesicles. So now we are ready to process this liposomal sample. A few things to note prior to processing the sample. The system has already been primed, and we have submerged the cooling coil in an ice water bath. So I'm going to go ahead and introduce the sample to the system. So there currently is some volume of water in the system. So what we're going to do is once we start the motor and the intensifier, we're going to collect a few strokes to waste, and these few strokes will just be of water. Once we see a color change in the outlet sample, that's how we know that we have actual sample, and we will begin to collect that sample. So I'm going to go ahead and start the motor and the intensifier. So you can see we've collected sample after one pass, and it is much more translucent than the unprocessed or the pre-processed sample. This is indicative that we are beginning to get some of those smaller sized particles, which is a good sign. So what we're going to do is we're going to reintroduce this sample to process for an additional pass. I'm going to introduce the sample into the inlet reservoir. We again have a certain volume of sample already in the process piping, so we're going to go ahead and collect that sample, reintroduce that volume, and then start collecting the actual second pass. So I'm going to reintroduce the first pass, start the motor and the intensifier. Select the hold-up volume. So we've collected the second pass. What we are going to do is we're going to reintroduce it to the system, process, collect the hold-up volume, reintroduce that, and then we would collect the third pass. And this is the process that you would follow for as many passes as you would need in order to achieve a liposomal sample
with the correct characteristics.
You can see from the left to the right, we have the unprocessed sample, a sample that was processed for 1 pass, and sample that was processed for 3 passes. You can see that the samples gradually get more translucent with additional passes, which correlates with the reduction in the particle size of the liposomes.
Great, so now that you all hopefully have a better understanding of what processing a liposomal formulation on a microfluidizer processor might look like, we're going to get into a few specific case studies. So these first couple of case studies were again done in collaboration with our collaborators at the University of Strathclyde. And they're actually pretty exciting because the first 2 case studies were done in manufacturing in a solvent-free process. So again, as I had mentioned previously, if you are to use the thin film hydration process, this does involve the use of solvents. And typically these solvents can actually be quite nasty, such as chloroform. So you can potentially run into issues there due to the toxicity of the solvent, along with the fact that if you utilize a solvent, you need to have an additional step included in your process to remove that solvent. So for these reasons, finding a solvent-free manufacturing process for producing liposomes can actually be quite beneficial. And what this process might look like, again, is a pretty similar pre-mixing procedure, but rather than using a lipid film, you can use a lipid mixture in the form of a powder instead. Hydrate that in an aqueous buffer by utilizing a high-shear mixer and making sure that you're above the transition temperature of the lipids. At this point, again, you will form kind of those MLVs. You can then process through the microfluidizer processor. There's an additional buffer exchange or purification step, where in the case of hydrophilic drugs, this is the step where the drug would actually be loaded into the liposome. There's kind of some clarification steps in here as well. And then you can sterilize the liposome by passing through a 0.2 micron filter. So in this first particular case study, we were looking at liposomal doxorubicin. So doxorubicin, again, is a hydrophilic active. And specifically, we're looking at pegylated liposomes incorporating this doxorubicin. Again, kind of the purpose of pegylating the liposomes is to increase the circulation half-life. So we've listed the formulation here, and kind of what we show in this first image are the liposomes that are produced immediately after processing through the microfluidizer processor. So while it's tough with the scale bar to see what the exact size of these liposomes are, it is an encouraging sign to see that a majority of the liposomes seem to be in a similar size range. So the image here on the bottom right is after the actual drug loading of the doxorubicin. And doxorubicin actually has an interesting property in that it crystallizes once it is kind of inside of that aqueous core of the liposome. So that's what you're seeing here with these sort of rectangular structures. And it is again, a really encouraging sign that a vast majority, if not all of the liposomes shown in this image do contain that rectangular structure, which indicates a very high level of drug loading. And then you can see right here an image of the sample itself. It's this very bright red color, which is a property of doxorubicin. So looking at some of the results, again, in this particular case study, our collaborators at the University of Strathclyde varied a handful of processing conditions, including the processing pressure. So they process at both 18,000 and 20,000 PSI, as well as by doing a different number of passes at both of these pressures. So they ran at both 2 and 3 passes at both 18,000 and 20,000 PSI. You can see when you're looking at the initial liposomes that were formed, when you're processing at 20,000 PSI, the particle size is a little bit smaller, which is to be expected, as when you're processing at this higher pressure, you're subjecting the liposomes to a higher level of shear. But in any case, they're all relatively small, relatively good sized liposomes in about the 80 to 100 nanometer range, with a pretty good PDI of around 0.2 as well. So it's then encouraging to see when they perform the purification step, kind of giving a charge to the system, that none of these, neither the particle size nor the PDI was really significantly altered. So it's kind of a good sign and shows the integrity of the liposomes that were formed. The next step was the drug loading step, which again kind of gives some encouraging signs as the particle size, PDI, and zeta potential all seem relatively unaffected. And then you can see that there's high levels of drug loading as well, close to 100%. And again, the final stage here was the sterilization phase. So passing these liposomes through a 0.2 micron filter. And again, it's really encouraging to see that even after this step, kind of the particle size, PDI, zeta potential, and drug loading percentage all remain relatively the same. So it's encouraging that they were able to kind of create these liposomes with a good size and a high level of drug loading, but they also wanted to look into the drug release rates of these liposomes. And what they found is that while the slight differences in the formulations of the liposome itself did not really alter the drug release rate all that significantly, what they did show is that when you're able to formulate these liposomal forms of doxorubicin and compare their release rate to the release rate of free doxorubicin, they were able to show that it's a much more controlled release. So you can see, for example, with all of these liposomal formulations, after 6 hours, you're only looking at around a 50 to 60% doxorubicin release, whereas if you were to introduce free doxorubicin, you essentially have a 100% release after just 2 hours. So doxorubicin was a hydrophilic drug, but we also ran an additional case study utilizing a hydrophobic drug, the aforementioned amphotericin B. So as this is a hydrophobic drug, the manufacturing process does look slightly different. The main difference is that the amphotericin B was actually included in the initial lipid mixture. So essentially when you're adding the lipid mixture in the form of a powder to an aqueous buffer, the amphotericin B was included with that mixture. So that when you are creating these MLVs by utilizing a high-shear premixer and you're above the lipid transition temperature, these MLVs will actually encapsulate the amphotericin B within their lipid bilayer. So then you can process through the microfluidizer processor, as shown before, and in your outlet, you'll be left with these SUVs that already have the amphotericin B encapsulated. So the results of this case study were really promising. As you can see, after 3 passes, the particle size was able to be brought down to around 100 nanometers with a pretty good PDI as well. And the zeta potential again stayed relatively constant throughout processing, which is a good sign. The drug loading was initially at 100% in the pre-processing, and it stayed around that level throughout processing as well, which is again a good sign. You're not losing any of the drug while you're processing through the microfluidizer processor. These liposomes were also sterile filtered. And again, it's good to see that after that sterile filter process, the size remains fairly small at 106 nanometers with a pretty good PDI of around 0.2, and you have a very high drug loading percentage as well at around 98. And then the image here in the bottom right is just kind of a microscope image of what these liposomes might look like. So for my final case study, kind of concerning liposomes, we're looking at an API that was utilized to treat carcinomas. And this liposomal formulation kind of containing this API was initially formulated on one of our pilot scale microfluidizer processors, the M110EH microfluidizer processor. And the goal of this case study was to scale up this optimized process from the M110EH to the M7250 microfluidizer processor. So from the pilot scale to the production scale. So on the M110EH, an F12Y interaction chamber was utilized, and the sample was processed at 30,000 PSI for 12 passes. And the results, as you can see, were an average particle size of around 43 nanometers with a PDI of around of below 0.1, which is a pretty solid distribution. So again, when we went to scale up on the M7250 microfluidizer, we kept all of these processing conditions the same. So again, you can see we utilized the same interaction chamber, the F12Y. The -6 here just indicates that there were 6 of those microchannels in parallel, which allows for a higher throughput. The processing pressure was kept the same at 30,000 PSI, and the formulation was processed for the same number of passes as well. And what you can see is that the results are almost identical with a Z average right around 43 nanometers and a PDI below 0.1. When you overlay these distributions as well, you can see that they almost perfectly overlap upon one another, which again demonstrates the scalability of the microfluidizer processor, in this case specifically when processing a liposomal formulation, indicating that as long as you're keeping your formulation the same and your processing conditions the same, that you will be able to get the exact same results regardless of the scale on which you are processing. So those were all the slides I had pertaining to liposomes, but as it's a bit of a hot topic right now and the formulation and the processing technique is relatively similar to the formulation of liposomes, I wanted to briefly touch on lipid nanoparticles as well. So lipid nanoparticles can absolutely be manufactured utilizing a microfluidizer processor. And there's kind of two approaches that can be utilized to do so. So the first approach is a two-step approach, which again is kind of similar to manufacturing liposomes in that you hydrate the lipids, utilize a high-shear mixer to create a premix, process through the microfluidizer processor, and you can then be left with these empty lipid nanoparticles. And then at this stage, once these empty lipid nanoparticles have been formed, you can kind of complex your genetic material. In this case, in this particular case study, which we again ran in conjunction with our collaborators at the University of Strathclyde, that genetic material that was tested was DNA. But you can also potentially run a one-step in situ encapsulation, with the difference being you include the genetic material in your premix. So when you're initially, again, hydrating your lipids, utilizing a high-shear rotor-stator mixer or other high-shear mixer, your genetic material will kind of already be encapsulated within these lipid nanoparticles. So then at this stage, you can utilize the microfluidizer processor to size reduce these particles, and what you're left with are lipid nanoparticles with your genetic material, again, in this particular case, DNA, kind of already encapsulated. We recommend the two-step approach for a variety of reasons, mostly around the fact that when you are creating these empty lipid nanoparticles, they tend to be more stable and kind of require less severe storage conditions than if you are to actually manufacture the fully formulated lipid nanoparticles. Additionally, as they are more stable, you can then just complex the genetic material, again, in this particular case, DNA, as needed. And in these instances, it can actually be very useful in response to a pandemic type situation where you can kind of create a backstock of the empty lipid nanoparticles and then again, just complex the genetic material as needed. So in this particular case study, our collaborators at the University of Strathclyde tested both methods, and both methods proved to be quite successful. So for the two-step approach, the initial liposomes the initial lipid nanoparticles that were formed had a really small size with a really good PDI, so a really small size around 50 nanometers with a PDI kind of between 0.2 and 0.3. And then what they did is they played with the negative to positive ratio, which is essentially the ratio of the DNA to the cationic lipids. And what they found is kind of a negative to positive ratio of right around 4 was the sweet spot that kind of gave the smallest particle size with a pretty good PDI as well. You can see the zeta potential wasn't, again, significantly affected by this kind of negative to positive ratio. And kind of regardless of which ratio they use, there's a high DNA loading percentage, which is obviously a good sign, as the goal of this approach is to load DNA into the particles themselves. So our collaborators also tested the one-step approach, keeping that negative to positive ratio constant at 4. And this approach also yielded fairly encouraging results. As you can see, when they processed for both 3 and 4 passes, they were left with small particles with a good PDI. The zeta potential wasn't significantly altered by the number of passes, which is a good sign. It kind of shows the integrity of the particles themselves. And then again, after 1, 2, 3, and 4 passes, the DNA loading percentage remains quite high, quite close to 100%. So these are all kind of gave really encouraging results. So that's kind of all I had on the technical side of things, but I really quickly kind of wanted to point your attention to how we as an applications team, so myself and Young, who is also on the line, kind of help our customers. So We have an applications lab located in our facility just outside of Boston, Massachusetts. And as you can see kind of in this first image, we have our full product line available to us in this lab, and we have a variety of analysis techniques as well. So what we do in our lab is we provide 3 paid services for our customers, and those include proof of concept testing, process optimization testing, and scale-up testing. And through running these tests with our customers and kind of being in constant communication with our customers, we're kind of able to keep our finger on the pulse of what some emerging applications are that utilize a microfluidizer processor. And I've listed some of those applications below. So if you have any questions about liposomes or any of these applications, feel free to reach out to myself, Nejla, Christina, or Young, and also feel free to ask any questions right now. Thank you.
Thank you, Chris, for a very informative and clear presentation and nice video. It's all clear, I guess, because no questions up to now. We can wait for a few minutes. And if you just want to contact us, please, after presentation, you can contact us from your email addresses or telephone numbers. Şu ana kadar soru göremedim ben, soru gelmedi ama sorularınız olursa bize her zaman ulaşabilirsiniz. Telefon numaralarımız ve e-mail adreslerimiz şu an görünüyor ekranda. Chris biraz bahsetti aslında nasıl birlikte geliştirdiğimiz aplikasyonları. Bize başvurduğunuz takdirde öncelikle sizinle bir görüşme yapıyoruz. Numuneleriniz ve uygulamalarınızla ilgili bilgiler alıyoruz ve birlikte bu süreci yürütüyoruz. Yes, we can share the seminar slides. One question from Emre Fatih Edis. I think we will be able to share the presentation shortly, right, Yunus?
Yes, sure.
Okay. Yeah, we had the confirmation from our marketing department. Yes, we will be able to share the seminar slides. And I think we will also share in YouTube, our YouTube channel.
Correct.
Right. Okay. So any other questions? Yes. Merhaba Mustafa Hoca. Is it possible to use organic solvents in fluidizer? I think the question is to Chris.
Oh yeah, it's certainly possible to utilize them within the microfluidizer processor. There are some considerations you want to kind of keep in mind. We do have a variety of elastomers within the system. So while a majority of the, I guess, process piping is stainless steel, so it can certainly kind of withstand organic solvents, there are just a handful of elastomers within the system. So depending on which solvent you would like to use, if you just kind of check in with us or Animed, to confirm that it won't damage any of those elastomers, they can certainly be utilized within the microfluidizer.
Right, thank you. Chris'in de açıkladığı şekilde aslında daha detaylı olarak sizinle uygulama gereksinimlerini konuşuyoruz. Hatta denemeler de yapabiliyoruz. Dolayısıyla bize ulaşmanızı bekliyoruz. Mustafa Hocam her zaman.
Sorry, I just want to add a quick comment here.
Oh, please,
yeah. Yeah, so as Chris has mentioned, so the compatibility issue usually will not be a concern because our systems are designed to handle a variety of different solvents. But if this question is related to if you need to use solvent to form liposomes, so the answer will be yes and no. So as Chris has introduced during the presentation, like normally you don't need to use solvent. I know some other method that would require to use a solvent stream to form liposomes. However, as you can see in a variety of case studies we've showed there, you don't have to, I mean, there may be a solvent step before our process you may have to use to generate the lipid mixture, but in general, you don't need to use solvent. However, I do hear from some customers that it is also possible to use a small amount of solvent, kind of like similar to the solvent way. So that is possible, but it's not necessary, in my opinion.
Hocam sorumuza cevap oldu sanıyorum. Belki başka uygulamalar için de sordum. Çünkü Fluidizer'da kullanmak mümkün mü diye. Evet, sorunun cevabı evet. Ama daha detaylı olarak elbette uygulamayı bilmek istiyoruz. Other questions? Yeah, to Yang, this is for you.
So the question is, product shelf life is very short in nanoliposomal coatings. How long can the shelf life of the product be extended with this machine? This is an interesting question. So I guess from what Chris had introduced about the capabilities, I guess one thing we could contribute, or the microfluidizer technology can contribute to increase the shelf life, is to provide you the liposome samples or vesicles with more uniform distribution. So in that regard, to try to increase the stability. But I suspect if the instability or shorter shelf life is coming from formulation or maybe storage condition that may or may not related to the production method. So you may have to you may want to optimize your either your formulation or look into the storage condition. I know, for example, some of the commercial available drugs are, try to increase their shelf life is they lyophilize the product afterwards to remove water, excessive water from the product. So that's a great way to try to extend the shelf life of the products.
Okay, thank you. Sunum boyunca katılım hep yüksekti. Şu anda da hala görüyorum. Buradasınız. Sorularınız varsa birkaç dakika daha bekleyelim. Yoksa sunumu paylaşacağımızın sözünü vermiştik zaten. Ayrıca YouTube kanalımızdan da bizi takip edebilirsiniz. Yine e-mail ile bize ulaşabilirsiniz her zaman. Biz teşekkür ederiz. Türkçe'de bu arada sorular sorulabilir. Varsa. Başka soru olmadığını görüyorum. Ben bu güzel takıma çok teşekkür ediyorum. Çünkü hepimiz ayrı yerlerden bağlandık. Türkiye'den, Almanya'dan, Amerika'dan. Güzel bir sunum oldu. Teşekkür ediyoruz katılımlarınız için. Sanıyorum burada bitireceğiz. Başka soru gelmedi. Hepinize çok sağlıklı ve güzel günler diliyoruz. İnşallah önümüzdeki süreçte bu toplantılarımızı belki yüz yüze de yapabiliyor olacağız. 2 yıl öncesinde olduğu gibi. Teşekkürler ve görüşmek üzere. Thank you for great team. Thank you for whole contribution and support. Thank you.